Thank you for the introduction. Yeah, I'm a faculty member in the Department of Electrical Engineering, and again, I'm here presenting on behalf of David Lynes, who is the first author of this work. He is not able to attend this conference, unfortunately. So I will just jump directly to the motivation behind this work. So first, we would like to reduce the size, weight, power consumption, and cost of the critical for aerospace system where these factors are highly constrained. Our compact sensors are also designed for mobile surveillance, combining portability with high performance. And furthermore, we also aim to improve the sensor performance by engineering materials to improve the resonator's quality factor. This directly leads to more sensitive measurements and overall enhanced sensor operation. And the ability to maintain consistent performance across extreme temperatures was also another important objective of this work. This is crucial for ensuring reliability in harsh environmental conditions. And finally, the dual resonator modes enable self-referencing, which compensates for temperature variations, ensuring more accurate measurements in dynamic conditions. Now, let's explore the working principle of our MEMS resonators. On the left here, we have finite element analysis simulation of two adjacent mechanical modes that we call second contour mode and the fundamental width extensional mode. These modes are transduced by 500 nanometer aluminum nitride layer deposited on 10 micron thick silicon layer. We fabricated two sets of resonator, which is with and without oxide film, as you can see in here. The dimensions were carefully designed so that the two adjacent modes are close in frequency to simplify the calibration and characterization. On the right here, we can see the harmonic response. The solid lines represent the resonators with the oxide layer, while the dashed lines show the resonator response without it. The oxide film improves the quality factors by acting as a buffer layer, smoothing surface defects, and enhancing bonding between silicon and aluminum nitride. Now, let's take a look at the fabrication process of the MEMS resonators. This was carried out by an external foundry, Science Corporation. So in the top views here, we can see the two resonators designed both with input and output electrodes. On the left side here, we see the resonator with 200 nanometer silicon dioxide layer, shown in red color, and without it on the right side here. In both cases, 500 nanometer aluminum nitride layer depicted in pink used as the electromechanical transducer layer, and the aluminum electrodes are shown in green. The silicon dioxide layer serves as an insulating layer and also plays a crucial role in acting as a buffer layer, smoothing the surface defects and enhancing the bonding between silicon and aluminum nitride. This helps to enhance the device quality factor. All the structures were fabricated using CMOS compatible processes at Science Corporation, making the technology scalable for larger application. Now, on this slide here, we present the colorized SEM images of our fabricated resonators. On the left is the aluminum nitride on silicon dioxide on silicon resonators. And on the right, we have the aluminum nitride on silicon structure without the oxide layer. This. So we can see the oxide layer is highlighted in red color there, and we don't have any oxide in this resonator. So in both cases, the resonators have been fully released, allowing them to vibrate freely. And again, as we mentioned earlier, the oxide layer there plays a critical role in acting as a buffer layer, smoothing the surface defects and enhancing bonding between silicon and aluminum nitride transducer. So this slide shows the measurement setup we use to characterize the performance of our fabricated resonators. The device under test here was placed inside a Lakeshore vacuum probe station, where we conducted 2-port S parameter measurements over a broad range of temperature from -200 up to 200 degrees Celsius using liquid nitrogen for cooling. So the vacuum pump here is used to maintain a low pressure environment at around 1 microtorr, effectively minimizing the air damping. A standard RF short open loop through calibration was performed to remove any errors from the cables and probes, ensuring precise data acquisition. And the network analyzer was used to capture the resonator's response across this temperature range, allowing us to access the quality factor, resonant frequency, and overall performance of this extreme condition. So these are the measurement results from the 2-port S parameter characterization of our fabricated resonators. The blue curve represents the resonator with the oxide layer, and the red curve shows the resonators without it. Since both resonators have the same lateral dimension, the addition of the oxide layers shifts the frequency down. This is because the effective acoustic velocity is lower due to the oxide layer, which reduces the resonant frequency for both the second contour mode as well as the width extensional mode, fundamental mode. The oxide layer significantly enhances the quality factor, with the resonator achieving 6-fold of improvement in the maximum quality factor compared to the version without the oxide layer. This improvement directly translates into increased sensitivity, which is critical for accurate sensing in various applications. So here we present the 2-port S parameter measurement results for our resonators over a wide temperature range, from -200 up to 200 degrees Celsius. On the left here, we have the resonators without an oxide layer, and on the right, we have the resonator with an oxide layer. As temperature changes, we observe frequency shift for both second contour mode and the first width extensional mode. Despite the oxide layer lowering the overall resonant frequency due to reduced effective acoustic velocity, the temperature coefficient of frequency, or the TCF, is nearly identical for both resonators. The presence of the oxide layer does not significantly alter the TCF, as evidenced by the consistent frequency shift in both cases. So what stands out, however, is the oxide layer resonator enhanced Q factor, which directly improves the sensitivity across the entire temperature range. These results demonstrate the clear advantage of the oxide layer in improving the resonator's performance without compromising temperature stability. So here, this graph shows the temperature coefficient of frequency measurement results for the resonator over a wide temperature range from -200 up to 200 degrees Celsius. So on the left here, we have the TCF for the first with extensional mode, and on the right here, we have the TCF for the second contour mode. So the blue points represent the resonators with an oxide layer, while the red crosses represent the resonators without the oxide. So as we can see here, the TCF for both configuration follows similar trend demonstrating that the addition of the oxide layer does not significantly alter the TCF across the temperature range. So to summarize, our approach leverages dual mechanical modes to provide a self-referencing temperature-independent sensing platform, which significantly enhances the measurement accuracy. By incorporating the oxide layer, we have achieved more than 6-fold of improvement in quality factor, leading to superior overall sensor performance. And the resonator consistently perform across extreme temperature range from negative 200 degrees Celsius up to 200 degrees Celsius, making it ideal for application in harsh environments. And looking ahead, we plan to explore multi-parameter sensing further in multi-parameter sensing for to prove the versatility and applicability of this platform for a broader range of sensing needs. That concludes our presentation today, and I'll be happy to answer any questions you may have.